Okay, so last time we had the first week and we talked about limits. So let me quickly review what we did last time. And we start with new techniques of limits, then we'll pass to continuity. So this is probably our last week before we start the main topic of derivatives. Okay, so we talked about limits. So the main concept we were trying to understand was, what does it mean to say what is limit of a function as the parameter approaches a certain value is equal to L mean. Okay, so what is this? Okay, so here we want to say that the values of f remain close to the value L around x sub 0. Okay, not only at x sub 0. In fact, we are not interested at what happens at x sub 0. That will come later. We will compare the values of f near L and the value of f at L. Okay, so those are two different concepts. We want to say that the values of f remain close to L around x sub 0. Okay, so you see there are two vague expressions here, close to L and around x sub 0. Okay, so close to L means that we decide how much close is close enough. Okay, so we say if f of x minus L, the difference between f of x and L is less than epsilon, then it is close enough. Okay? And we choose, the important thing is we choose this epsilon at will. Okay, so there's nothing which restricts us to decide how much close is close enough. You can choose this very large, in which case it will not be interesting, but then you are also allowed to choose it as small as you like, which makes this interesting. And around x sub 0 means that corresponding to this epsilon, okay, so it's traditional to write epsilon positive. So, for example, in a party, if you yell out epsilon is negative and two people fall down and faint, they are mathematicians. Okay, so epsilon must be positive, and it must be written like this. Corresponding to this epsilon, we find okay, we didn't mention open, so we find the neighborhood of x sub 0 as, okay, so we draw the picture. This is x sub 0. On this part, we have x sub 0 minus delta. On this part, x sub 0 plus delta. This is the x-axis. We consider this interval. We don't consider this point. We consider this, okay? Such that here we have any x here, x minus x sub 0 is less than delta, but we don't want it to be the center point, such that, okay, so let me call this star, this thing, such that star holds for all x here. Okay, so here is this picture or this algebraic expression. Okay, so you see that this is a concept. This is a definition. the definition does not tell you how to find L. The whole idea is to find L. And later, using this L, we will talk about the derivative of a function. So if the function f of x is simple, if you can guess what L will be, then it is not difficult to show that you can find this delta if the limit actually exists. But the function f must be very simple. Okay, if the function is a little bit complicated, you do what you naturally do in science or engineering. You divide the problem into smaller parts. You try to solve all the small parts and then put it together. So that thing we call theorems about limits. Okay, so theorems about limits. So these things could be summarized as sum of a limit. So limit of a sum. Sum is the sum of limits. Okay, limit of f plus g is the limit of f plus limit of g. So if you have a long addition, you can calculate the limits of each part and add them together. So instead of this sum, you can talk about product. Product of a limit is the product of limits. And limit of a constant times f is, so here these are blocks, and you have the same thing here, constant times f. So with these things, for example, now you can immediately calculate the limit of a polynomial without much difficulty, because all you have to do here is just check that limit of c as x goes to wherever it likes is c, and limit of x as x goes to x sub 0 is x sub 0. Okay, check means that check if you can do this. Choose an arbitrary f. Can you find the delta such that under these conditions this will hold? Okay, so in both of these things, limit of a constant and limit of x, that's trivial. Okay, so you just write it down and it works by itself. So now you can calculate the limit of any polynomial. Okay, so if px is a polynomial, then limit, okay, so let me say then, so that we understand. Next week when we read this, we understand. Then limit of x goes to x sub 0 of p of x is p of x sub 0. Okay, so for example, first of all, I know that the limit of a polynomial is going to be the sum of the limits of each term. Each term is a constant times x to the power something. So that constant will come out, and all I have to do is find the limit of x to the power something. Okay, so x to the power something is power something of x. Okay, x squared, for example, I know that limit of x is x squared, so limit of x squared using this will be x sub 0 squared, etc. Okay, so using these things, I immediately calculate the limit of a polynomial without using any epsilon delta. That's the whole idea. Okay, so your epsilon delta is your last resource because it's not easy to to apply. Okay, so you are paying a price here. This epsilon delta definition is very precise. Everybody understands exactly the same thing. Okay, but to achieve this precision, you have to pay a price. Well, maybe you don't have, but we pay a price. It is practically useless. You cannot do calculations with this for reasonable functions. Okay, so one more thing here, continuing like this. Ratio ratio of a limit is the ratio of limits. Okay. Well, of course, when we are saying ratio, we are not expecting that anybody will divide by 0. So those things are always written in detail here. If the limit of the denominator is different than 0, then you apply this. Okay, but we leave it to everybody's understanding. And then the last thing, which we can prove using this thing easily is roots. Root of a nth root, fifth root of a limit of a nth root is the nth root of the limit. Okay, so let me say this thing is this of the same thing. Okay. So these things, when you say theorem, this is the idea of a theorem is always the same thing. You have a precise, a beautiful theorem, which is useless. The theorem says that under certain conditions, you can use the theorem like this. So now, after this, you can forget the theorem, you can forget the proof, you use these conditions. Okay? The only important thing here is you have to understand under which conditions the theorem is proved so that you don't try to apply the theorem in a position where it's not applicable. For example, if the denominator is 0, you don't say, oh, I saw it in a theorem, I'll divide by 0. Okay? So that's why we prove these things and read them carefully to understand. Okay, so far, so good. Now we can, after this ratio, we can prove that the limit of a rational function is limit of the ratios. Okay. Limit of p of x over q of x as x goes to x sub 0. So here, p and q polynomials, and q x sub 0 is different than 0. Okay? So I know that by just looking at this theorem without doing any epsilon delta calculation, this is p of x sub 0 over q of x sub 0. Okay, so roots are easy to understand. Okay, so you can take the root of this, no problem. Okay, so this is, I think, what we did last time. This is the summary of what we did last time. And we also said that if most of the problems that we could solve are of the form where you have p of x over q of x, but both p of x sub 0 is 0 and q of x sub 0 is 0. Okay? Since these are polynomials, it means that x minus x sub 0 divides both of them. So you divide them, cancel x minus x sub 0s, try again. Okay? So you reach to a position where q of x sub 0 is different than 0. Okay? And then you just evaluate this. That is the limit. If it turns out that, well, since these are polynomials, you will be able to go up to the point where q of x sub 0 is different than 0. Okay, so that was the only tricky problem we had. So we also had some high school type problems where these are not polynomials, but this is root of something minus something. So you have to multiply it with the conjugate, simplify, and you will bring it, you again bring it to a polynomial form. Okay, so that was, these are the only things that we could solve with the first week's techniques. So this week we'll start with the squeeze theorem or sandwich theorem. Okay, so new techniques. Well, actually, we will have just the sandwich theorem. Okay, so let f of x be strictly less than g of x around x sub 0. Okay, so possibly not. Okay, possibly not at x sub 0. Okay, so we call such things punctured neighborhood. Okay, so a neighborhood of the form. So let me draw the picture. So this is x sub 0. We leave it out. This is x sub 0 minus delta. So we don't have this. x sub 0 plus delta, we don't have this. We only consider these parts. Okay, so you only take x in this shaded region. This is the picture. Algebraically, we write this like this. Okay, so the distance between x and x sub 0 is less than delta, means that x cannot be chosen here or here because that's too far away. And this tells us that in this picture we don't want x sub 0. Okay? A neighborhood of this form is called a punctured neighborhood. Okay, so punctured means there's a hole put into the neighborhood. Okay, so we are looking at the case where f is always less than or equal to g of x in a punctured neighborhood of x sub 0. This also it means that maybe if you move away from x sub 0, this relation will no longer hold. Since we are interested in what happens around x sub 0, we don't care what happens away from x sub 0. If there is a regularity that we can observe around x sub 0, we write it. Okay, so that's the meaning of all this garbage. I'm writing this only once to set our terminology. Then, limit of f of x as x goes to x sub 0 is less than or equal to limit of g of x as x goes to x sub 0 when both limits exist. So in math books, in calculus, for example, you will always see a security sentence like this. Okay, so that means that if the limit does not exist, normally you will just leave it there. Okay, so you don't do anything if the limit does not exist. But the author does not want to take any responsibility, so you have to, if you are writing a book, you have to tell that the limit exists. It's just like those warnings on on pill boxes where it says if you drink too much of this, you die. Okay, nobody drinks too much of this, but the company must write it there. So it's something like this. Okay, so to prove such a thing, well, we are not interested in the proof, but the idea in the proof is something that we also use sometimes in the problems. Okay, so here the idea of proof of such things. Okay, such things is a very vague thing, but such things is to check what happens to, say, g of x minus f of x as x approaches to x sub 0. Okay? So sometimes, for example, we want to show in the exercises that the limit of this is equal to the limit of this. It's not easy to work it like this, okay? But you look at the difference. If this is going to be, if this limit is going to be equal to this limit, then you want to show that the difference goes to 0. To show that the difference is 0 is much easier than working with these things because you take the absolute value of this and you check if it is going to be smaller than anything you can think of. Okay? So in this case, we want to show that the limit of this is never going to be negative. The limit of this is going to be positive or 0. Okay? So of course we will not prove this here, but this idea of taking the difference and instead of calculating two limits, just working on a single limit makes life much easier, even though theoretically you are still working with this and still working with this. But practically it becomes easy. Okay, so the same thing will happen in a minute. We will talk about continuous functions. We will say that a continuous function is a function whose limit is equal to its value. Okay, and then we say, why are we interested in continuous function? The answer is because it's easy to calculate limits with them. But then that's how you found them. First you have to know that its limit is equal to itself. Then you say that this is going to make life easier. Theoretically, that's nonsense, but practically it works. Okay, because again, by some theorems like this, we suddenly recognize a whole repertoire of continuous functions without doing any calculation, and now you can use them in limits without doing any calculation. So practically how it works. That's how it works. Okay, so this is this is one key theorem which is innocently looking and very simple, but that theorem is used in the background of proof of this theorem. Okay, so this is the squeeze theorem. And sometimes the sandwich theorem. Okay, so in some books they call it the squeeze theorem. In some books they call it the sandwich theorem. So if you are looking at different books, don't be surprised, it's not a new theorem. So we have now three functions. So suppose f of x is less than or equal to g of x less than or equal to h of x on some punctured neighborhood of x sub 0. Okay, then, and also suppose limit of f of x as x goes to x sub 0, limit of h of x as x goes to x sub 0 exists and are both equal to the same number. Çok yaşa. Okay, so we suppose that these two limits exist and are the same, and we call it L. Okay, then the limit of this exists. Limit of g of x as x goes to x sub 0 exists and is L. Okay, so this is again a very typical theorem format. Basic idea is to calculate limits. The definition of limit is epsilon delta, very complicated, practically useless. So the theorem says that now I pour in lots of extra information and then suddenly you know the limit. Okay, so the the extra information here is that I'm trying to understand this limit. Okay, it is complicated, but I see that I can throw away some of the complicated parts in it, which we will do in the examples. And then that is one of the simple parts is smaller than this, and one of the simple parts, after if you throw something else, it is larger than this, always, in some neighborhood of x sub 0. And we also don't care about x sub 0, but we also put that condition here because most of the time this is useful when there is no way of plugging in x equals x sub 0 here. It is undefined. You always have 1 over x minus x sub 0 here. You'll always have 0 divisor here. It's not a polynomial. You cannot cancel it. Okay? But somehow you can squeeze it between two reasonably understandable functions. And another information is that these functions are such that I can calculate their limits. Those limits exist, and I know, and it turns out those limits are the same. Okay, so for example, they can be polynomials. You immediately plug in the value, as we did here, and you get the same number. Okay, so under these lots of extra conditions, you don't have to do any epsilon delta calculation. The theorem says the limit of this is automatically L. Okay, so we will not do the proof, but in the proof, you see that you use this part there, and you use this part there. You take the limit. You look at this minus this, and this minus this. Okay, so those things you do patiently once, and then the theorem falls out. So it's not a mysterious theorem. And the typical example for this is, let me say, prototype example is the following. Let g of x is equal to x sine 1 over x when x is different than 0. So we don't define, this function is not defined at x equals 0. So last time we looked at the graph of this and we realized that it cannot be defined in a nice way at x sub 0. Okay, because this thing cannot be defined at x equals 0. Okay, and even the limit of this does not exist. Okay, so but we are hoping that if we multiply it with x, it will tame it. Okay, so now in this expression, there is no way to cancel out the indeterminacy. At x equals 0, the function is not defined. Okay, but I can find h of x and f of x, which bounds this from below and above. Okay, so note that. So what is the question here? What is limit as x goes to 0 of x sine 1 over x if the limit exists? Okay, so maybe the limit does not exist. We have lots of examples where the limit does not exist. Okay, so we check this with the squeeze theorem or sandwich theorem. Okay, so we notice that no matter how complicated sine 1 over x is, sine 1 over x it is never going to be equal to 5, right? It's never going to be equal to minus 7. It's always going to remain between minus 1 and plus 1. Okay? Its values are always between minus 1 and plus 1. Okay? So this is one of the main applications of the sandwich theorem. You have a very complicated looking function which you cannot do anything. But you notice that this guy is tamed. It doesn't go to infinity, or it doesn't go to minus infinity. Okay? So then you just take it out and put the upper bound for it. Now you have a very nice function for sine 1 over x, plus or minus 1. Okay? That is sine 1 over x is less than 1, larger than minus 1. Okay? Of course, x is different than 0. So now you multiply both sides with x. If x is positive, you have minus x sine 1 over x less than x. If x is negative, then everything is turned around, but you again have the same inequality. Okay? So now this is something that we can immediately apply the sandwich theorem, okay? Because you see that the sandwich theorem looks like as if it is invented for this function. I know the limit of this wherever it goes. I know the limit of this wherever it goes. Okay? So in this particular example, of course, the limit of this function is not interesting if x is different than 0. Okay? Well, at this point, we don't know how to do this theoretically, but sine 1 over x is a continuous function if x is different than 0. So you just put in the value here, you put the value here, that's the limit. In fact, you can also guess correctly by drawing the graph of this. The graph of this is bad, only looks complicated only at 0. At other points, it's a very nice continuous graph. Okay? So in this case, we just now take the limits. Okay. Limit as x goes to 0 of x is equal to 0. Limit of minus x as x goes to 0 is 0. So by the sandwich theorem, limit x goes to 0 of x sine 1 over x must be 0. Okay? The graph of this function you can always remember to use Wolfram alpha. You just put this function at Wolfram alpha and say plot it, and you'll get an idea about the picture. So let's say This is x-axis, this is y-axis. Now, this function is always between these functions. So we plot the graph of these functions first. This is the y equals x function. And this is the y equals minus x function. The function x times sine 1 over x is in between here. Okay, so let me start from here. So it will probably be something like this. And we know that it will get complicated here. Okay, so as it approaches the origin, it oscillates infinitely many times on this side, and it oscillates infinitely many times on the other side. But by even looking at the picture, we know that the graph is approaching to 0 as x approaches to 0. Okay, now normally when we are applying the sandwich theorem, we don't write all of these things, because no matter which function you choose here, you will start to explain that you notice that it is between two functions, two numbers, or two nice things. You multiply do something and bring it to this. You have to give these explanations and the graph. We don't do this, okay? You do this once, we understand. So shorthand for applying the sandwich theorem is the following. Okay, so you say x sine 1 over x. Okay, so we know that this is less than or equal to, so I forgot these equalities. Okay, so these are equalities. Okay, so this is less than or equal to x, larger than or equal to minus x. I know that the limit of this is 0, and the limit of this is 0 as x goes to 0. Then we say dot, 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 this goes to 0, okay? So this picture, okay, so this picture is shorthand, a Chinese character for all of this explanation, okay? So this is, when you write this, people understand that you are considering the limit as x goes to 0. These things both apply, go to 0. You check that, and it follows from the sandwich theorem that this thing also must go to 0. Okay, so this is how we apply this is how we show to others that we applied the sandwich theorem. Okay. Any questions so far? So everything is crystal clear? Okay, so on Friday we'll have a surprise quiz, so I'm expecting everybody to get full marks. Since you don't have any questions, that means you totally understood this. Okay? So some people are smiling, means that you have a question. Okay, let's see. Okay, so we have, let me write a very similar problem again. Okay, so for example, limit as x goes to 0, x to the 4 cosine pi over x cubed. Okay, so this is as complicated as you can get. Once you understand the general idea, when you look at this thing, you immediately see that cosine of something, doesn't matter what that something is always between -1 and +1, wherever it is defined. In this case, it's not defined at 0. Well, okay, so that's what we are trying to understand. What's the limit of this as x goes to 0? So this part will never cause any problem in the limit, because it will always oscillate between -1 and +1. And it is hit by this guy who definitely goes to 0. So this guy will take this to 0 with it. Okay? So this is, if this is the question, you also write cosine pi over x cubed is less than or equal to 1, larger than or equal to -1 when x is different than 0. We don't even bother to draw the graph, okay, because the graph will not be useful. Here we did it just to show off that we totally understand it. If something is easy, you show off. If something is difficult, then you just pour in a theorem and you said, I'll leave it to the reader to understand these things. Okay, so we multiply everything by x to the 4. Of course, in these things you have to consider the signs, but in this case it is easy, so I'm not I'm not checking the sign. Okay, so we know that this is true. Okay, so now I'll use this shorthand. Clearly, this goes to 0, and this goes to 0 as x goes to 0. Therefore, this goes to 0. Okay, so that's that's the end of this. So I have some silly looking thing here. Okay, so limit to make life look difficult. Let's approach to 0 only from one side. Okay, and then square root of x. Okay, so that's why we are approaching the limit from the right. Square root of x must be a real number. Then I multiply this 3 plus 7 sine cube 8 pi over 15 x to the power. Okay, let me write it a little bit big. 15x. Okay, let's make it square. Let's put cube here. Okay, square here. Okay, so this is as complicated as we can get. Okay, so you see that this is an example where I cannot put in x equals 0 because of this 0 division here, which cannot be resolved. Okay, so we expect that since this is going to 0, and since this is probably oscillating between something and something, okay, so this guy will take it to 0. Okay, so we suspect that the limit will be 0. So before solving any math problem, first you must have a guess. It is not necessary that you make the correct guess. Okay, it doesn't matter whether your guess is correct or wrong. You make a guess, then you try to show that your guess is correct. Okay, if you can show it, you are done. If you cannot show it, while you are in the process of trying to show that this wrong guess will hold, you learn a few things. You get more familiar with the function, and you say, okay, my guess was wrong. I'll make another guess. Okay, so you don't pay money for making new guesses. But if you don't make a guess, if you just start playing around with this, as most of you will probably do in the midterm exam, while reading your paper, will get very annoyed and will put a red cross on your paper, and then you'll come and ask us why we didn't give you any marks. So I'm explaining you why we are not giving you any partial credits. Okay, it must be your calculations must be directed towards a certain end. It doesn't matter if that end is correct or not, because if you could do something in a direction, you'll learn something, and then you'll find the correct way. If that is not correct, you'll find the correct way. But if you just play around, okay, you get lost. That's why we make these suggestions. Otherwise, you can do anything you like. So here, without any proof, without any reasoning, I made the guess that this will go to 0. It may be correct, it may not be correct. But now I'll try to show that it is 0. If it works, it works. If it doesn't, we'll learn something and we'll refine our guess. Okay, so how do I do this? Okay, so let me first show you how we professionally do this. So it doesn't matter. I have numbers here. I know that this doesn't go to infinity. Okay, as x goes to 0, this function will remain between -1 and +1. Okay, so this behaves like sine 1 over x. Okay, so you put some power there, you put 8 pi, etc. It doesn't matter. It just shifts the graph. Okay, what happens is that it keeps oscillating infinitely many times as x approaches to the origin, but it never becomes 10. It never becomes -500. It is bounded. Okay, so the key word is bounded. Okay, so this part is bounded. I multiply a bounded thing by 7. It's again bounded. It doesn't go to infinity. I add a small number, or I can add 3 million here. It doesn't matter. Okay, let's make this horrible. Let's make this more than the number of molecules in the universe. Okay, it is bounded. It is finite. It's not infinite. Okay, so there's a difference between a huge number and infinity. One of them is a mere finite number. So this part, after I take even the square of this, okay, let's take a very huge power of this. Okay, so here I have a very huge number, positive or negative, but it is less than, it's a finite number, less than infinite. Okay, that's all I need. Okay, so this is this is something you must do in such calculations, because you will break your back trying to find a nice sharp upper bound for this, and then you will realize that you never use the value of that upper bound. All you are doing is you are multiplying that upper bound by 0. Okay, so why did I calculate that precise upper bound for this? So I don't. Okay, that's where experience comes in. Since I'm going to apply squeeze theorem to this, I'll multiply the limit of this by the upper bound of this. Upper bound of this is a number. What do I use about the property of the upper bound? Just that it is a finite number. Okay, so I don't need precisely the maximum or minimum of this function, because I'll just multiply it by 0. Okay, so here we notice that, so let me, instead of writing again, so let me put this, okay. We notice that this number, this function is bounded. Okay, so that is, there is a number m such that this function, okay, so let's call this, okay, so absolute value of this function is less than or equal to m. Again, in such cases, you never write strictly less than here, because strictly less than is a claim saying that this function will never be equal to this. We don't need that claim, so you say just less than or equal to, which doesn't make any more claim saying that this will never be larger than this. Okay? Then we have square root of x times this function. Okay? We take the absolute value of this. Okay? So this is less than or equal to, well, here I'm taking the positive square root, so I have this m. Okay? An absolute value is always larger than or equal to 0. Okay, so here I immediately find myself in the domain of squeeze theorem. Okay? This function is a constant. The limit of a constant function is always 0 wherever you go. Okay, so this goes to 0. So this is a function times a constant. So one of the theorems says that ignore the constant, just take the limit of this and then multiply by this constant. Limit of a root is again one of the theorems. Limit of x as x goes to 0 is 0. Root is 0 times constant is 0. So this goes to 0 as x goes to 0. So sandwich theorem now tells me that this is 0. I am one tiny step away from saying that the limit of this is 0. Okay? If the limit of the absolute value of a function goes to 0, the limit of the function cannot be 1. Okay? Because if it was 1, then you take the absolute value of this, it would be 1. Okay? So if the limit of the absolute value of a function is 0, the function also goes to 0. Okay? Next, we use the obvious fact that limit of f of x as x goes to something is 0 if and only if. So this means both sides are the same. Limit as x goes to x sub 0 of the absolute value of this is 0. This equals 0. Okay? So from here, hence, in our example, limit as x goes to, okay, so here I have plus so that this works. Limit as x goes to 0 from the right of square root of x times this function is equal to 0. Okay, I use this because I proved it. I calculated this part, which says that the limit of this must be 0, and this is 0. Okay, so traditionally, you must end your answers in the exams also, or wherever you are writing, by putting the last sentence saying that whatever you were trying to achieve is achieved. Okay, so this is a 2,300-year tradition. Okay, 2,300 years ago, Euclid started this tradition. In the beginning of a proof, he says, then I want to prove this, and after a page, generally his proofs are short, but after one page of proof, he says, I proved this. Okay, so that's the scientific tradition. Therefore, at the end, we have to write this. Okay, any questions so far? Okay, so let me check what we will do. I was planning to solve an example, but that's going to take too long. Okay, let's take a break here. Next hour, I'll start with continuity.